Assalamualaikum and good morning. I bid to all lecturers and students. Nice to meet you all. Allow me to introduce myself. My name is Muhammad Ismail bin Muhammad Isa, and today I will present to you guys a research paper which is titled Synthesis and Characterization of Hydrophobic Property of Silicon Dioxide in Palm Oil-Based Biocoating. Okay, to understand more about this project, let's explore on how conventional polyurethane was made. Polyurethane are formed by reacting a polyol and with a diisocyanate in the presence of suitable catalyst and additive. A different type of polyol and diisocyanate mixture give various different of characteristic to the mixture. Because of its versatility and easy to modify, it has been used in different type of application such as foam in cushions, sealant for rooftop, wood adhesive, and floor polish. However, the conventional process uses a lot of petroleum-based raw material. As time goes by, the petroleum prices are becoming more expensive and could be depleted one day. Production of synthetic polyol and diisocyanate give a lot of toxic waste that can threaten the environment. Many researchers are becoming aware about this situation and striving to replace synthetic polyurethane with bio-based as alternative to reduce petroleum source dependency and enhance the biodegradability. One of the alternative is various type of vegetable oil such as castor oil and jastrofa oil was converted to polyol to replace the petroleum-based polyol. In this project, palm oil acrylate will be used as a substitute to polyol and silicon dioxide will be added as a hydrophobic agent. The objective of this research are to synthesize and characterize biocoating from epoxidized palm oil and to study the effect of different silicon dioxide loading on hydrophobicity properties of palm oil-based polyurethane. And then we go to the scope of study. The scope of study in this research are to synthesize biocoating from the epoxidized palm oil, characterize the structure of palm oil-based polyurethane before and after addition of silicon dioxide by using FTIR analysis. The last one is to study the effect of different silicon dioxide loading on hydrophobic performance by water absorption test and water sliding test. The sample was prepared by was started by reaction of epoxidized palm oil with acrylic acid at a ratio of 1 to 9. Triethylamine and hydroquinone was added to the beaker as inhibitor and catalyst. The reaction was last about 16 hours at 110 degrees. After that, the sample was washed with distilled water using rotary evaporator at 95 degrees Celsius. And now, we will react the palm oil acrylate with diisocyanate. 1 mole of hydroxyethylamine and 1 mole of isophorone diisocyanate was mixed with palm oil acrylate at room temperature. Hydroquinone and dibutyl dilaurate were added earlier as catalyst. The solution was mixed for 15 minutes. Lastly, the silicon dioxide at different amount will be added into palm oil-based polyurethane and mixed. Then, the other monomer were also added such as trimethyl propane triacrylate and 1,6-hexanediol diacrylate. Benzophenone were added as photoinitiator. The solution was mixed at 60 degrees Celsius until fully miscible and then cured under UV light. The sample will undergo several analyses, which are FTIR analysis, water sliding angle test, and water absorption test. For FTIR analysis, the liquid sample was dropped between two potassium bromide discs and slot into the cell for FTIR analysis. The sample was scanned for 16 times and FTIR spectra were recorded. For water sliding angle test, the sample plates were inclined at 25-degree angle. Then a drop of water droplet was placed onto the top of the coated surface using microsyringe. The time taken for the water to slide down until the end of plate was recorded. The step were repeated twice to get the average. For water absorption test, firstly, the initial wake of sample were recorded. Then the sample was submerged in water and left for 52 hours, which is 3 days. The sample then were removed from water and dry with tissue before wetted every 24 hours. Then the percent of absorption were calculated. After doing several analyses, firstly, we are going to look at the FTIR analysis result. The figure shows FTIR result for all the samples. The first line at the topmost is for epoxidized palm oil. The second line is for acrylated epoxidized palm oil. The third line is palm oil based polyurethane. And the fourth is for polyurethane with addition of silicon dioxide. Based on the epoxidized palm oil spectra, the first one, there is presence of COC functional group at wave number 835.82. From that spectra, we can prove that this is epoxidized palm oil because the structure comprises of carboxyl group at the front. For the second line, which is for acrylated palm oil, we can see that there is new peak emerged at wave number 829 and 1600. This indicates there is existence of C double bond C functional group. This means a successful acrylation process because the acrylation process open the epoxide ring and forming double bond with the palm oil structure. For the third line, which is for palm oil based polyurethane, we see there are new peaks at 2265, 1714, 1531, and 1186 that shows the existence of isocyanate, carbonyl group, and amine. From all of these three peaks, we can say that there is urethane group formed in the structure, and this shows the polyurethane chain has been successfully formed. For the fourth line of the spectra, which is for palm oil based polyurethane after addition of silicon dioxide, there are new peaks emerge at 800, 1100, 1250, and 2800. All of that peak can be identified as silicon oxide group. This can indicate that there is addition of silicon dioxide to the system. Next, we test the coating for its hydrophobic properties. First, we do the water sliding angle test. From the result obtained, we can see that when there are absence of silicon dioxide in the mixture, the time taken for the water droplet to slide down is the slowest, which is about 40.75 seconds. As we add silicon dioxide to polyurethane, we can see at the minimum amount, which is 0.3 pHr, it decreased the time taken for water droplet to 14.55 seconds. As we add more silicon dioxide to the coating, the time taken for water droplet to slide down decrease. The fastest time recorded is at the highest amount of silicon dioxide addition, which is at 3.0 pHr, which is 11.95 seconds. From this graph, we can say that the higher silicon dioxide addition resulting lower time taken for the water droplet to slide down. This indicates that addition of more silicon dioxide make water easily mobile on the surface. This mobility can be related to lower surface energy on the coating. Lower surface energy reduce the attractive force between the coating and water molecule. This phenomenon can be related to the silicon dioxide non-polar properties, as non-polar molecule is an excellent compound for repelling water. Thus, the addition of silicon dioxide improves the hydrophobicity of palm oil polyurethane. For water absorption test, we can observe that the absorption percentage is the highest when no silicon dioxide added to polyurethane, which is about 20% absorption. When we start add silicon dioxide to the mixture, the absorption percentage decrease, and the lowest absorption recorded, which is about 5.93% at the highest amount of silicon dioxide, which is 3.0 pHr. This lower absorption means water molecules are now difficult to enter the coating. This can be related to higher cross-linking between polyurethane change, resulting higher density of the coating. The water molecules are now harder to diffuse inside the structure of the coating. Thus, the addition of silicon dioxide improves the hydrophobicity of palm oil polyurethane. As a conclusion, palm oil-based polyurethane with addition of silicon dioxide as hydrophobic agent was successfully synthesized. Characterization of palm oil-based polyurethane using FTIR show the evidence of ring opening and accretion process that indicate successful palm oil-based polyurethane formation. And characterization of palm oil-based polyurethane after addition of silicon dioxide using FTIR show the existence of silicon dioxide in the structure. And the effect of silicon dioxide loading on hydrophobicity performance by water absorption test and water sliding angle test was successfully carried out. The highest amount of silicon dioxide show better performance in both tests. That's all from me, and thank you for your attention. And now I will open to Q&A session.